Welcome to the hypothesis testing video. This is an introduction. So far we have covered sampling distributions and estimation, to be more specific, confidence intervals. So using all that knowledge from the two previous units, now we're going to start making it a little bit more formal with the hypothesis testing. So in general, a hypothesis is just an assertion concerning one or more populations. So here are some examples of hypotheses. The proportion of delayed flights is 10%. So what we're saying here, or the hypothesis, is that P, the parameter, the proportion of the parameter, is 0.1. A second example is the lifetime of a product A, it's equal to the lifetime of product B. So we're saying that the difference between 1 and B, so mu1 minus mu2, or mu A minus mu B to be more specific, is equal to 0, because we're saying that they are the same, right? The next example is the average weight is at least 30 pounds. So that's mu is greater or equal 30, right? So these are examples of hypotheses that we can write in order to check if they are true or if they are not. Now, the hypothesis test requires two hypotheses. So every time we're going to set a problem and we're going to solve it, first we need to define what are our two hypotheses. So we will have what we call the null hypothesis and the alternative hypothesis. So H0 represents the null and H1 represents the alternative. Now, how are we going to define which one is the null and which one is the alternative? So one easy way to do that is that the equality or the equal sign has to be always included in the null hypothesis. That means that in the null hypothesis we'll have expressions such as mu greater or equal, for example, 100. Another example will be h0 equal to mu less equal than 100, or in a different problem we might have mu equal to 100. So please notice that the equal sign it's always included in the null hypothesis. If we have an expression such as mu greater than 100, that's not that's not the null hypothesis. That will be an alternative hypothesis. Mu less than 100 or mu different than 100. Again, in the null hypothesis, it is not possible to have these expressions. We will only have expressions where the equal sign is included. Alright, so let's try to analyze how's the conclusion in the hypothesis test. So there are two possible results. So once we have set the hypothesis, there are two possibilities. First, we reject the null hypothesis in favor of the alternative hypothesis. Or the second alternative is that we do not reject the null hypothesis with a confidence level that is defined. So again, you reject the null hypothesis or you don't reject the null hypothesis. So usually we don't use the term we accept the null hypothesis. The equivalent here in statistics is we do not reject the null hypothesis. Now, what are the steps in the hypothesis testing? So first, we're going to define both hypotheses, the null and the alternative one. It is required a significance level because this will give us our confidence level, right? 1 minus alpha is the confidence level. Then we will find the statistic. So that means z, t, chi-square, or Fisher, depending on the parameter that we're using in our hypothesis. Step 4, we make a decision. So we're gonna either reject or we don't reject the null hypothesis. That will depend, of course, of where is located our test statistic. And at the end, of course, the last step will be to make the interpretation. So to answer the question in the problem. So let's go over the different steps. Step 1. First, we're going to define the null and alternative hypothesis. So we might have one-sided test or two-sided test. So theta might be any parameter. So we have an example of one side is theta is less equal than a specific value, and of course then the alternative hypothesis will be the complement, and this is important. Every time you define the null and alternative hypothesis, you gotta know that one is the complement of the other one. Therefore, we're going to include all the possibilities with these two hypotheses. Second option is theta greater equal than a specific value, therefore the alternative is the complement, right? Theta less than that same value. In the two-sided case, if we have that the parameter is equal to a specific value, then the alternative will be different, right? That's the complement. So here there are some guidelines to identify, like once you're given a problem, so how are you gonna find which one is the sign that is required. So let's see. So if the question involves less equal or greater equal, so some examples are at least means greater equal, right? Or at most, that will be at maximum, that's less equal. Those two expressions, at least or at most, they include the equal sign, right? They include the equal sign. Therefore, you will define first the null hypothesis, and of course, the complement will be the alternative hypothesis. Now, if the question involves only less or greater, for example, the mean value is less than 40, so the equal sign is not included in that expression. Therefore, you are going to define first the alternative hypothesis, because remember, we don't have the equal sign here, so you define first the hypothesis, the alternative hypothesis, and of course the complement will be the null hypothesis. If the question does not involve inequalities, then we will use the equal sign for the null hypothesis, and the different symbol will be for the alternative hypothesis. So let's practice. That's step number 1. And the first question is the percentage of defective items is at most 5%. So at most is less equal, right? It's like a limit, it's like a maximum value. Then the equal sign is included, therefore this question will go straight to the null hypothesis. So that's why we have p less equal 0.05, and of course the alternative hypothesis will be the complement. Second example, the percentage of defective items is at least 5%. So this is greater equal, right? So equal sign included, then we define first the null hypothesis. The third one, the percentage of defective items is exactly equal to 5%. So equal sign, it goes straight to the null hypothesis. And of course the complement is the alternative hypothesis. The percentage of defective items is less than 5%. So less, the equal sign is not included. Therefore, we cannot use that expression straight into the null hypothesis. So we go to alternative first, we define p less than 0.05, and then of course the complement greater equal will be our null hypothesis. The last example is the percentage of defective items is greater without the equal sign than 5%. So same thing, right? We first define the alternative, greater, and then the complement will be less equal. Here we're given some problems, and we're asked to please define both hypotheses. So let's read them. A manufacturer of a certain brand of rice cereal claims that the average saturated fat content does not exceed 1.5 grams per serving. State the null and alternative hypothesis to be used in testing this claim. So the manufacturer is claiming that the percentage does not exceed, right? The content does not exceed 1.5 grams. So that's mu, is referring to this parameter, because it's talking about the average saturated fat, right? So that's mu. does not exist less equal 1.5. So I'm using null hypothesis because the equal sign is included, and of course then the alternative will be the complement, so that the average content of fat is greater than 1.5. An important thing to mention is that in the null and alternative hypothesis, we always write down only parameters. So that means mu, sigma, sigma square, p, or a difference or a ratio. It is not possible to have x bar or s or something like that. Why not? Because this is sample information. And when you are trying to make an inference, it's about a parameter. It's about a population value. That's why you will never see x bar, s, or p hat, or a difference between two x bars in one of the hypotheses. That's just not possible, so be careful when you are setting the two hypotheses. Okay, the second example, a real estate agent claims that 60% of all private residences being built today are 3-bedroom homes. To test these claims, a large sample of new residents inspected. The proportion of these homes with 3 bedrooms is recorded and used as the test statistic. State the null and alternative hypothesis to be used in the test and determine the location of the critical region. Alright, so here the claim is that a proportion, that's P, is equal to 0.6, right? So this will be the null hypothesis, the quality is included, the equal sign. And of course the alternative is that the proportion is different than 0.6. So this is step number 1, define the null and alternative hypothesis. The second step is easy in general because it's just to define the level of significance. So in the class it's given, and in real life you can define it on your own. So most of the times it will be 0.05, some cases 0.1, or even 0.01, because that will give us confidence level of 90%, 95%, and 99%, and those are the most popular values. Now, there are two errors that you need to be aware of. So one, it's called the type 1 error. So when are you getting the type 1 error, or when it's possible a type 1 error? Imagine that the null hypothesis is true, right? It's true, but you reject the null hypothesis. So if that occurs, then you are incurring in type 1 error. If the null hypothesis is true and you don't reject the null hypothesis, of course, you are making the right decision. Now, if the null hypothesis is false and you reject the null hypothesis, again, you are making the right decision. But if the null hypothesis is false and you don't detect that and you do not reject the null hypothesis, then that's what we call the type 2 error. So type 1 error is rejection of the null hypothesis when it is true, and type 2 error is non-rejection of the null hypothesis when it is false. It can be visualized in a nice plot, which we are gonna cover in one of the problems at the end of the unit. This won't be included in this video. So some key elements: alpha is the level of significance, or it's also known as the type 1 error. We will see why later in the next plot. The confidence level is the complement 1 minus alpha. Beta is how we call the type 2 error. So remember, type 2 error is when we don't reject the null hypothesis, even though it's false. And the complement of beta is what we call the power of the test. So is the probability to reject the null hypothesis given that the null hypothesis is false. So that's when you identify that the null hypothesis is not true. In this plot, it summarizes these concepts. So in the first one, this is the first figure, right? The first bell. imagine that this is true. Let's say that this is we're trying to make an inference about mu, and even if mu it's the same as h sub 0 as the null hypothesis, it is possible that we get an area here. We can get a statistic in this small area, this blue area. But even though it's following the original shape, the original bell, it is possible to get a statistic that is located in the blue area. So if we're getting a statistic in the blue area, then we're gonna reject the null hypothesis, even though the null hypothesis is true, even though we shouldn't reject. So that's what we call type 1 error, and it's represented in the original shape, in the original bell. Now, when the null hypothesis is not true, so let's say that the mean value has shifted, so now what is true is the alternative hypothesis, and of course you don't know that. Then if we do not reject the null hypothesis, even though it has changed, that's what we call the type 2 error. Please notice that the type 2 error is measured in the second plot. Why is measured in the second plot? Because the true value has changed. The true value is not mu, it's mu prime. It's different. H1 is the one that is true. That's why the type 2 error it's measured as a probability in the second plot, not in the first one. I know this is an abstract concept right now, but as we start solving problems in this unit, and at the end again of the unit, we will solve some examples where we calculate type 1 and type 2 errors. It will make more sense. Step 3 is the test statistic. That will depend, of course, of the parameter that we are trying to analyze. So if it's mu, mean, the mean value, then the test statistic will be either z or t. If it's variance or standard deviation sigma, then we will use chi-square. Sampling distributions, right? Proportion, we can use binomial or z. Means difference, z or t. Variance ratio, we use Fisher. Proportion difference, we use z if the conditions are satisfied. So this is important. We need the test statistics in order to find probabilities, in order to find whether we should accept or reject. Step 4 is where we make a decision. In step 4, we check if we are in the rejection region or not. So there are two approaches. Strategy 1, it's we need to define the critical region in this case, and there is a step 2, which is the p-value. Now, what is first? We need to define what is the critical region or rejection area. First, that critical region is going to be always defined by the alternative hypothesis. So the alternative hypothesis is going to be always pointing towards the rejection area. For example, here is parameter greater than one value. So the greater means that the rejection area is going to be to the right. It doesn't matter which probability distribution we're using. If the rejection area is greater, then if the alternative hypothesis is using the greater symbol, then it's going to the right. If we have the less than, then the rejection area is going to be to the left. Again, the alternative hypothesis is always pointing towards the rejection area. And of course, if we have different, so that will be a two-sided test. That means that we will have rejection area to the right and rejection area to the left. So how are we going to make the decision? So once we find the statistic, which can be z from the previous step, t, chi-square or Fisher, depending on the problem, then we will plot or we will check if we are outside the rejection area. If our test statistic is outside the rejection area, then we do not reject the null hypothesis. But if, let's say, that our test statistic is within the rejection area, of course, we're going to reject the null hypothesis with the confidence level that is defined. So this is one option, or strategy one, to make a decision. There is a second alternative, which is called the p-value, and I would say that this one is more popular, especially when you're using software. Is the fastest way to make a decision. To compute the p-value, to get the p-value, which is a probability, you need to know where is located the rejection area. So if we read the definition of the p-value, it doesn't make a lot of sense at the beginning. It says that it's the lowest level of significance at which the observed value of the test statistic is significant. So it's like a riddle, right, at this point. But let me show you an idea on how it works. So this is our probability sampling distribution. Then imagine that we have a alternative hypothesis that says something like mu greater than 100, for example. So since it's greater than the alternative hypothesis, then the rejection area goes to the right. The rejection area, the area, it's alpha, significance level. So it's going to be like 0.05, 0.1, or 0.01, depending on the problem. So if our test statistic, let's say, is located here in this region, that's our z or t, depending on the situation, we are not in the rejection area, right? We are not going to reject the hypothesis. Now, how is measured the p-value? So to measure the p-value, we always need the test statistic, and we need to identify where is the rejection area. So in this case, we have the test statistic, and then we measure the p-value as the probability towards the rejection area. So we measure from the t to up to positive infinity, right, to the right. So if you notice, the shaded area, or the p-value, because that's the p-value, the area in this case to the right of our test statistic, is greater than the rejection area, because the rejection area, it's only here, this portion here. So our blue area is bigger than that. Then the decision, if the p-value is greater than alpha, like in this case, then that is that we do not reject the null hypothesis, and it makes sense because we are not in the rejection area. We are not in the rejection region, right? Now, if the opposite occurs, so let me change even the distribution, it doesn't matter which distribution is, the analysis is the same. Imagine that this is a test where the rejection area is to the left. That means that the alternative hypothesis is less than, right? Less than. So now, if we find our test statistic, let's say that is F, Fisher, and it's located in the rejection area. Here is our F. Now, if we measure the p-value, it's always measured towards the rejection area. So it's measured to the left because the rejection area is to the left. So let me shade it a little bit. Is this one? This will be the p-value, the area to the left of the Fisher statistic that we found. Since that p-value is smaller than the rejection area, than alpha, it's smaller than alpha, then the decision is that we reject the null hypothesis. That's why you will find here this rule. If the p-value is less than alpha, we reject the null hypothesis because we are in the rejection region. But if the p-value is greater than alpha, then the null hypothesis is not rejected, meaning that our test statistic is outside that rejection region. Of course, we're going to practice a little bit more using these concepts in the next video.